Hello everyone, and welcome to this lecture of the Graduate School of the Symposium on Geometry Processing. Thanks for looking this lecture on the functional representation of 3D shapes and high frequencies. I am Simone Melzi, and unfortunately this year we cannot meet in person at SGP, so let me start with an introduction on me. So I did my PhD at the University of Verona. My supervisor was Umberto Castellani, and during my PhD, I studied the signal processing technique and the extension and definition of these tools on non-Euclidean domain. After my PhD, I did 2 years of postdoc at the same university, and then I moved to Paris at École Polytechnique in the team of Max Ovsyannikov, where I did 6 months of postdoc. And then now I am a postdoc at the University of Rome, Sapienza University of Rome, in the team of Emanuele Rodola. And during my postdoc, I mainly work on shape matching and 3D shape registration. In this lecture, we will see how starting from the reality, we can acquire 3D data like the geometry of these ores. And in geometry processing, it's useful to look not only at the geometry but also to function define over the surface of the object. And in particular, we will focus on functions that contain high frequencies. And why we want to do that? The main motivation is the shape correspondence task. So given a pair of shape, the shape correspondence is the problem to find a point-to-point map between the two shapes that associate to each vertex, each point on the first shape, a corresponding point on the second shape. Usually we visualize the correspondence through color coding, as in this example, where corresponding points are depicted with the same color. So shape correspondence problem is a huge problem due to the combinatorial definition of this problem. We want to find the good permutation to align each point from the first surface to each point of the second. And our solution that has been proposed for shape correspondence is based on the functional representation, and this solution is functional maps. We will see functional maps during this lecture, but let's see some application for the shape correspondence. And standard application are the formation transfer in the context of animation, or statistical shape analysis, registration and parameterization, and anomaly detection in the context of medical imaging. So the lecture is organized as follows. I will start with an introduction and notation section. Then I will present the functional spaces and Fourier representation, both for the 1D domain and for 3D shapes. Then I will present the functional shape correspondence method, the functional maps, as we say. And finally, I will focus on high frequencies, looking at the problems related with high frequencies and the proposed solution. Let's start with introduction and notation. First of all, what is a shape? In the continuous setting, a shape is a two-dimensional smooth manifold embedded in the three-dimensional space. In this lecture, we will consider only connected shape, so shapes that have not disconnected components, and these shapes can have or not, they can eventually have a boundary. In the discrete setting, a shape is represented by a collection of points in the 3D space, in this case n points, and in geometry processing, shapes are usually represented as polygonal meshes. In this lecture, we will only consider triangular meshes, where all the points in the 3D space are the vertices of this mesh, and these vertices are connected by edges, and these edges will compose a set of faces, and all these faces are triangles in our case. So we say that a shape is a manifold, and this implies that not more than two faces share a common edge, and so one edge is shared by a maximum of two faces, or by one face if it is a boundary edge. Now, what is a function? So from Wikipedia, we have the definition of function as a relation between two sets that associates to every element of the first set an element of the second set. Usually we refer to the element of the second set as the value. And as Wikipedia says, some typical examples are function from real number to real number. So let's start with such a kind of function. Here we consider an interval in the real line, that is minus pi, where we define this interval as a periodic interval. So we consider minus pi and pi as the same point. And what is a function is the association of one value of the first set, so the interval minus pi, with a value of the second set, the real line. Here we have such a kind of list of associated values, and this is a function that corresponds to this set of corresponding value. So in the discrete setting, we cannot consider a continuous function, and what we do is we sample a set of n elements on the first set. So in this case, in the interval minus pi, and we associate to each of these points the value that is given by the function. So we can start from the first sample and store the value of the function at this sample. Then we can move and store all the value for the selected point in a vector. And we do that for all the points in our sampling, and we obtain a discretization of the signal represented by a vector. The length of the vector is equal to the number of points that are selected on the interval minus pi, in this case n. So this is a discretization, and this discretization could be used for all functions defined on the same interval. So we use the same n points selected on the interval minus pi, and we can associate a vector to this other function. If we change the domain, in this case, if we consider the interval from 0 to 2 pi, we can sample the same number of points on this interval and represent the signal again as a vector of dimension with dimension n. So the only thing that is required to combine these two functions is the affine transformation between the two domains on which the functions are defined. And on the real line, this is an easy problem. One can compute the scaling and the translation to obtain to compare two functions defined on two different domains. Now, what is a function on a shape? So we can ideally think to a function as a set of value associated to each point on the surface. But in the discrete setting, we know that the surface is represented by a collection of points in the 3D space. And so a function is the corresponds to assign a value to each vertex in the mesh. In this case, we can consider the vertex number 127, and the value of the function at this point is equal to 1. So a function is defined in the same way on all the points. So at the vertex number 65, you have a different value, 0.25, and so on for all the vertices of the mesh. So with this definition of function, we can easily store the function in a vector as we did for the 1D function, and the order of the value inside the vector is given by the order of the vertices of the mesh. So the set of vertices are given in a precise order, and we can represent the function as a vector for which each entries correspond to the value of the function at the corresponding vertex. So for this mesh that has 772 vertices, the function f is represented by a vector of size 772. So remember that we say that a function is represented as a vector in the discrete setting, but we usually visualize the function in a smooth way. And here you can see some example of function defined on this shape, and a set of particular functions that can be considered are the coordinates of the 3D embedding of the shape. So in this case, you can see the x, here the y, and here the z. So just as a recap, what is the functional space defined on a 3D shape? So we say that each function can be represented as a vector with length equal to the number of vertices of the mesh. So if the mesh has n vertices, the function f corresponds to a vector in Rn, and the set of all the functions that can be considered on the shape are equal to Rn. This space of function is equipped with a set of operation as the standard function, and we can consider this operation as operation between vertices, between vectors. So that is defined. We can define the sum of two vectors, and this corresponds to the sum of functions, or the scalar product between a scalar value and a vector, and this corresponds to the scalar product for functions. And then we have the pointwise product between two vectors. So each element is multiplied with the corresponding element in the second vector, and this corresponds to the pointwise product in the functional space. Finally, we have the inner product between vector, and here I just want to highlight that this inner product depends on the geometry of the mesh. So a particular case that can be nice to consider is what happens if we have function defined on two different shapes, on two different domains. So we know that in the discrete setting, these functions are represented by the value of the function at each of the vertex of the two meshes. And so in this case, we have different vectors to represent the two functions. The two functions are similar but are defined on two different shapes, and the two shapes are represented by different meshes that has a different number of vertices. In this case, the moose on the left has 1000 vertices, while the tag on the right has 772 vertices. Moreover, the two meshes has a different order in the list of vertices. So the two vectors that represent these two similar functions are completely different. And as you can see, these two vector representations of the functions are not comparable at all. Let's continue with functional analysis and Fourier representation. Again, we will start from the 1D domain to see an example of what we want to see on 3D shape. So consider a function, or from now on we will say signal or function for the same object. So a signal f defined on the 1D interval minus pi, and a common result from signal processing is that a signal can be well approximated by a signal defined on a periodic domain such this can be well approximated as a linear combination of a given set of basis functions, and these basis functions are the Fourier basis. And as you can see, this function is represented by the linear combination of this function phi1, phi2, and phi3, and this Fourier basis function can be computed as the eigenfunction of the Euclidean Laplacian. So the Fourier basis is composed by these functions, and these functions are ordered with respect to their frequencies that correspond to the to how much each of these functions oscillates on the domain. So given a signal f defined on our domain, we can compute the set of coefficients as the inner product between the signal and each of the basis function. And then the synthesis of the signal is obtained as the linear combination of the basis function using the coefficient estimated during the analysis. So in the continuous case, the set of Fourier basis is infinite, and usually in real application only a subset of eigenfunctions are used to obtain the approximation of the signal, and we represent this finite number of basis function as k, and the functions that are used are the one associated to the frequencies with a smaller absolute value. And in the discrete setting, the number of Fourier bases is equal to the number of samples that we use to discretize the domain. And so the approximation is again given by a subset of k smaller than an eigenfunction. So due to this representation that use only the first Fourier basis, we obtain different level of representation depending on the number of Fourier bases that we are using to approximate the signal. In this case, you can see on the right the approximation of the signal visualized on the left with an increasing number of Fourier bases. As you can see, at the beginning, the signal is not well represented, and then adding more and more Fourier bases, we better approximate the signal. And at the end, when you use all the Fourier bases, in this case 100 Fourier bases due to the discretization of the considered domain, we completely recover the original signal. But with, for example, with 40 Fourier bases, as you can see, the approximation is not too bad, but a lot of details are lost. And this is the problem of low pass representation, that we are losing a lot of information that are contained in the high frequencies. And exactly these high frequencies are the one that we want to analyze in this lecture. Now, what is the Fourier analysis on 3D shape? So what we want to have is a set of functions defined on the 3D shape that can approximate any given function or signal defined on the surface as a linear combination. This is possible thanks to the Laplace-Beltrami operator the extension of the Euclidean Laplacian to non-Euclidean domain, and exactly the eigenfunctions of this operator can be used as an extension of the Fourier basis on non-Euclidean domain. Here on bottom we visualize the first five eigenfunction of the Laplace-Beltrami operator of this shape, and these eigenfunctions are orthonormal, so the inner product between each function and itself is equal to 1, while the inner product between two different eigenfunctions is equal to 0. And the eigenvalue associated to each of these eigenfunctions is correspond to how much the eigenfunction oscillates on the surface. And the eigenfunction can be sorted with respect to their corresponding eigenvalues that are all positive, all non-negative. The first one is equal to 0, and then they can be sorted in ascendant order. And as you can see, the function at the beginning is constant, and then the eigenfunction are more and more oscillating on the surface. So given a signal defined on the surface, we can again, as we did for the 1D domain, estimate the coefficient for the Fourier representation of the signal as the inner product between the signal and the eigenfunction of the Laplace-Beltrami operator that are the Fourier basis on 3D shape. And then the reconstruction of the signal can be obtained as a linear combination of the Fourier basis using these coefficients. And again, for smooth setting, for the continuous setting on smooth surface, the number of eigenfunction is equal to infinite, and usually only a subset of eigenfunction are used to approximate the signal. In the discrete setting, again, the number of eigenfunctions is equal to the number of vertices of the mesh, and also in this case, in real application, only the truncated subset of the first k smaller than an eigenfunction are used. And now let us see what is the LBO operator. So the LBO operator, as we said, is an extension of the Euclidean Laplacian to non-Euclidean domain, and the LBO approximates the sum of the second partial derivatives on the surface and could be explicitly defined as the divergence of the gradient of every function defined on the surface. Finally, the LBO operator is invariant to isometries, so maps that preserve geodesics. Here we need to introduce some additional notation. So what are geodesics? So given a couple of points P and Q on one surface, we define the geodesic between P and Q as the shortest path connecting P to Q, and this path should completely stay on the surface. So if we have a map between M and N, we can consider the image through this map of the 2 point P and Q, and T is an isometry if and only if it preserves the geodesic distance between the 2 point PQ and their images through T. So the Laplace-Beltrami operator is completely invariant to isometries. We have to say that in real application context, there are no real isometry. So there are shapes that can be connected by a map that is near to an isometry, but usually we don't find real isometries between discrete shapes. So the LBO in the discrete setting can be computed as the product of two matrices. So the inverse of omega, that is the mass matrix, and this matrix is a diagonal matrix that in which on the diagonal are stored the value of the area of the Barry cell associated to each vertex, and these Barry cells are obtained and connecting the barycenters of all the triangles that share the common vertex VI. Then W is the stiffness matrix and could be defined in several ways. In literature, you can find different definition of the stiffness matrix for the Laplace-Beltrami operator. One of the widely used is the cotangent ways, but we refer to the literature for additional details. So in the discrete setting, we need to add some additional notation. So the inner product that depend on the geometry of the shape can be computed using the mass matrix, and the middle of the inner product between the two vectors that represent the signals, and then we can store the truncated set of eigenfunction of the Laplace-Beltrami operator in a matrix phi, in which each column corresponds to a different eigenfunction, and they are usually stored in the order with respect to their eigenvalues. Then we can define the pseudo-inverse of this matrix phi as the matrix for which the product with phi is equal to 1. We refer to this pseudo-inverse as the phi dagger. And in the case of the eigenfunction of the Laplace-Beltrami operator, we know that these eigenfunctions are orthonormal, and so in this case, the pseudo-inverse is equal to the product of the transpose of phi times the mass matrix omega. So with this notation, we are able to write in a matrix notation the analysis and the synthesis for the Fourier representation of a signal f. So the coefficients are obtained as the product between the pseudo-inverse of the matrix phi and the signal f, and then the signal can be recovered as the product between the matrix phi and the coefficient. So as we saw for the 1D signal, also on for signal defined on surface, we have the problem of low pass representation. Here you can see the reconstruction of the signal on the left, and for different levels of low pass filter. And as you can see, adding more and more Fourier bases, we can recover the signal completely. But I want to highlight again that when we use only a few number of Fourier bases, we cannot completely recover the signal. So as you can see, in this case with 50 eigenfunction, we only are able to recover this smooth version of the function on the left. I would like to highlight again that a lot of details are lost. So you can see around the legs of the mouse, or all the high frequencies details that are spread over the surface. So now that we have the Fourier representation of surfaces, we have two main questions. So the first one is, if we have two different shapes, we saw that the discrete representation of signal on these two cannot be compared due to the different vectorization that depend on the different template that represent the two surfaces. So the question is, can we transfer a signal from one shape to another? And it seems that is not possible due to the different template that represent the two shapes. The second question is, now we have the Fourier representation of signals, and we can represent each signal on a shape as the set of coefficients that represent the signal in the Fourier basis. So if we have two shapes, as in this case, and we have two corresponding functions, so two functions that appear the same but defined on two different shapes, we can compute the coefficient for these two functions. And the question is, what is the relation between these two sets of coefficients? So we will answer to these two questions in the next section. And this section is about functional shape correspondence. So as we said at the beginning, shape correspondence is the problem to find a point-to-point map between a pair of shapes. And this problem is not easy to solve due to the combinatorial nature of the problem. And recently, a new solution has been proposed to solve this problem in the functional space. And we will describe this method that is the functional map framework. So if we consider these two shapes and a corresponding function defined on these two, what is a two corresponding functions? So two corresponding functions are two functions that that are corresponding in the sense that they arise from a point-to-point map. So if we have a point-to-point map T, the two functions g and f are corresponding function if for every point P in N, the value of g at P is equal to the value of f at the image through T of P. This is the meaning of corresponding function. So in the discrete setting, a point-to-point map can be represented by a matrix pi, for which each entry ij is equal to 1 if and only if t of I is equal to j. So now the point-to-point map T induces a functional map between the two shapes. So if we consider a function f defined on M, we can transfer this function on N, and this can be done and obtaining a function g defined on N, and this can be done through composition of the point-to-point map and the signal f. As you can see in the diagram on the right, starting from N, we can move to M through the point-to-point map T, and then f is defined on M, and the composition of T and f give us a function g that goes from N to the real set, the set of real numbers. And in the discrete setting, this transfer can be defined as the composition of f with the matrix pi that represents the point-to-point map. So we saw the Fourier representation for a function defined on 3D shapes, and in this case we can exploit the Fourier representation in the context of functional map by project the function f to its coefficients in the Fourier basis a, and we can do the same for the image of the function f through the functional map tf. So g is mapped to its coefficient in the Fourier basis of n, that is b. The functional map tf is represented in this setting as a matrix C that correspond to the change of basis from the Fourier basis of M to the Fourier basis on N. And so the coefficient B of the function G, that is the image of F through the functional maps, can be obtained as the product between this matrix C and the set of coefficient A from the function F on M. And the functional map matrix C can be estimated as the composition of these three matrices. So starting from the coefficient A of the function f, we can do the synthesis of the signal, multiplying the coefficient with the Fourier basis stored in the matrix phi. Then we can transfer the signal from the definition of the function g, applying the matrix pi, and finally we can project the signal transferred on the shape n, multiplying the signal with the pseudo inverse of the matrix phi n that correspond to compute the coefficient of this signal in the Fourier basis on n. And so the composition of these three matrices give us an explicit equation that can be used to compute the functional map C. So the problem is that our problem is to find the point-to-point correspondence that is encoded by pi, and we don't know both pi and C. So how to recover C and then how to obtain pi from C. So in the solution to estimate the matrix C is to consider a set of probe functions defined on the two shapes, and this function should be corresponding function. So we can use descriptors that are signature used to represent point, and these descriptors are usually defined in such a way that the different dimensionality of the descriptor correspond for two shapes that are similar, and corresponding point on these two shapes has the same value in this signature for the same scale. Other example of probe function that can be used are landmarks. Here we have a couple of low pass representation in the Fourier basis of two landmarks on the legs of the two or shapes, and these landmarks are usually given as a supervised input to the functional map pipeline. Once we have these two sets of corresponding functions defined on the two shapes, we can compute the coefficient in the Fourier basis for all these functions and store them as a column of a matrix A for the shape M, and the same can be done for the shape N, and we can store the coefficient of the Fourier basis for this set of probe function in a second matrix B. Then, once we have A and B, we can optimize for the best matrix C as the solution of this optimization problem, and this problem corresponds to the condition that the functional map C should preserve this set of corresponding function. So each function in the set of probe function of M should be mapped by the functional map C to the corresponding function in the set of probe function of the shapes N. Additionally, as you can see on the right, other constraints can be added, and these are usually referred as regularization of the functional map estimation, but in this lecture we will not focus on this regularization, and we refer to the literature for additional details. So once we have estimated the map C, how can we recover the point-to-point map between the two shapes? So we can consider a delta function defined on the shape M, and in this case the delta function is represented by delta x, and we can compute its coefficients in the Fourier basis. Thanks to the functional map C, we can transfer this coefficient to we can transfer this function to the space of function of the shape N, and this can be done multiplying the coefficient AX with the matrix C. And then we can reconstruct the transfer the signal, multiplying this coefficient with the Fourier basis phi n. Once we have this image through the functional map C, what we can do is to compare this image with all the delta function that can be defined on the shape n. And the corresponding point to the point x can be computed as the point that corresponds to the delta function that minimize this problem, and we can look to different delta function defined on the shape n on the right. And once we have the one that minimize the minimization problem, then we can assign to the point x is corresponding point y. I would highlight that this problem can be solved by nearest neighbor as a nearest neighbor problem in the space of the coefficient of delta function defined on the surface n, and we want to find the nearest neighbor to the image through the functional map C of the delta function delta x. So just to give a small recap of the functional maps pipeline, given two shapes m and n, we can compute the first k eigenfunction of the Laplace-Beltrami operator and store them in the matrices phi m and phi n. Usually k is in the interval between 30 and 100 as the number of eigenfunctions that are used. Then as a second step, we can compute a set of probe function for each of the shapes, and these probe function are usually landmarks or descriptor, as we said, and then we can store them, or better, their coefficients in the Fourier basis in two matrices A and B. Once we have these two matrices, we can solve the minimization problem defined by the constraint, the requirement that the function map should preserve this corresponding function, plus additional regularization that can be added. After the estimation of the functional map C, we can convert the functional map C to a point-to-point map T, solving the nearest neighbor assignment problem. Here we show some qualitative results of the correspondence that are obtained from the functional map framework. As I said at the beginning, the point-to-point map are represented by color coding, where corresponding points are depicted with the same color. So if you look at each pair that are visualized, they are colored in a comparable way. This means that the correspondence obtained from the functional map is meaningful. So for some quantitative evaluation, I briefly introduce a standard evaluation proposed in 2011 that is the cumulative curve of geodesic error. And this curve is obtained as follows. On the x-axis, we have the geodesic error, and on the y-axis, we have the percentage of the correct correspondences. So a point in these curves, for example, this point P, encodes the percentage of the correspondence that have an error that is equal or smaller to the value on the x-axis. In this case, these points say that the 85% of the points have an error that is equal or smaller to 0.25. The error is computed as the geodesic distance between the estimated corresponding point and the ground truth corresponding point. And finally, this geodesic error is normalized, taking the relative distance with respect to the maximum geodesic distance that can be computed between all the pairs of points of the shape. So as you can see, the functional map quantitative evaluation say that for the year in which it was proposed, it outperformed all the competitors. And to give an idea of the error that is obtained for these correspondences, we have this visualization on the right. Here you can see how wide is the an error of 0.025 as the blue point depicted on the shape, and the error of how wide is the error of 0.05 that is depicted as light blue on the human shape on the right. So if you remember, we end the previous section with a pair of questions. Now we know how signal defined on one shape can be transferred on a second shape, and this can be done by through the a point-to-point map or the functional maps that is induced by the point-to-point map. The second question that we had was, what is the relation between the set of coefficients in the Fourier basis for a pair of corresponding functions defined on two shapes? So relation is, so if you look at this example, you can see that these two shapes are similar, near isometrics, and so the composition of these signals in the Fourier basis is similar. So we have a similar set of coefficients, and only the coefficient number 5 are different because one is positive and the other is negative. And if we look to this visualization of the coefficient, you can see that from 1 to 30, the set of coefficient is quite different for the two shapes. And if we store this coefficient in a vector, as we did for the probe function, then we can see that the relation between these two sets of coefficients is given by the functional map C. So C times A should be equal to B. And the functional map C has this diagonal shape, and we can look to some insight of this shape of the functional map. So if we look at the first 5 value of on the diagonal of the functional map C, you can see that all the first 4 values are close to 1. This means that the coefficients are the same for the two shapes as we saw, and then the value in the position 5 on the diagonal is a negative value and is close to 1. This means that the sign of the coefficient is changed by the functional maps, and this corresponds to the flip in the sign of the eigenfunction of position 5. And as you can see, the right and left leg of the oars are colored with different color. On the top, we have the right leg that is colored in blue, and the left one is colored in orange, and the inverse on the bottom shape. So the value inside the functional map solve for these flips in the sign of the eigenfunction. Again, if we look to another part of the diagonal of the functional maps around position 15, we can see that there is a switch in the order of the eigenfunction. For example, here the eigenfunction 15 is inverted with the eigenfunction 16, and the functional maps as a non-diagonal shape in this case. Here around position 15 and 16, you can see that there is 2 orange positive value in the matrix that are not on in the diagonal. And this corresponds to the fact that the functional maps is telling us that to transform the coefficient of the shape M to the coefficient of the shape N, we need to switch the order of these two eigenfunctions. Okay, now that we have answered to our questions, we can consider the main subject of this lecture, that are high frequencies in the shape correspondence application. As we saw, the high frequencies have a huge impact in the Fourier representation of signal defined on 3D shapes, but also we can see the impact of high frequencies in the representation of point-to-point map when we adopt the functional map representation. So here we have a result from the original paper in which functional maps was proposed, and considering the ground truth point-to-point map between the source shape on the top and each of the four near isometric shapes, we look at the error in the representation of this point-to-point map with respect to the different number of eigenfunctions that are considered as a basis for the Fourier representation. As you can see, when we add more and more eigenfunction, the error decreases very quickly, and only when we reach 200 eigenfunction, we have a very small error. This means that when we are representing a point-to-point map in the functional map representation, we have a lot of error that is given by the selection of the Fourier basis, and in particular to the size of this Fourier basis. And this is completely similar to what we saw for the representation of signal. So a lot of information is lost due to the selection of the truncated subset of the Fourier basis, and this generates an error in the representation of the point-to-point map. So here we have visualization of this. So we are matching the shape on the right with the shape on the left, and we saw the representation of the ground truth point-to-point map between these two shapes for different number of Fourier bases used to represent the point-to-point map in the functional map representation. So when we start with one or two eigenfunction, the point-to-point map is very noisily represented, but then adding more and more eigenfunction, we can recover a more smooth and accurate point-to-point map. I would like to show you again a result in the middle with a functional map of size 60 times 60 that correspond to the selection of the Fourier basis on the two shapes with size 60. And as you can see, mainly on the legs, there are a lot of error. You can see the light pink legs for which a completely wrong mapping is provided in this scale. And if you remember, the results that we obtain with 200 Fourier basis is very accurate. So in shape correspondence, we have a trade-off between the number of Fourier bases that are considered and the quality or the complexity of the solution of the point-to-point matching problem. So if we consider a small set of Fourier bases, we have a low-pass representation, and this low-pass representation is positive due to the fact that it's easy to optimize for functional maps when we use only a small number of Fourier bases, due to the fact that the functional map in this case has a small size. And also for the optimization, a fewer number of probe functions are required. But from the negative side, this low pass representation, we saw that it loses a lot of details and provide a poor functional transfer or a not precise point-to-point map. With high frequencies, we have the positive aspect that the functions are better represented and we recover a lot of details, so we can have a good functional transfer between shapes. But at the same time, we have a huge negative aspect, that is that if we use a lot of Fourier bases in the representation of the point-to-point map, then the functional maps is not easy to estimate due to the large size and the large number of value that should be estimated. So in this case, also more probe functions are needed, and as we said, these probe functions are usually given as input. So this trade-off is an important trade-off in the functional representation of shape correspondences, and in the rest of this lecture we will see how this trade-off problem has been faced during the last years. In this section we will see some of the solutions that have been proposed to face this issue with the high frequencies in the representation of shape correspondence. The first idea is to exploit the algebraic structure of the functional spaces, and as we saw, these functional spaces on 3D shapes are equipped with a sum, a scalar product, and a pointwise product. So thanks to these operations, the structure of these functional spaces is an algebra. So we start from a theorem. So a functional maps that come from a point-to-point map should preserve the pointwise product of functions. What does it mean? It means that given a functional maps that come from a point-to-point map T, so we have the function map TF, for any product of function f1 and f2 on M, the image through the functional map TF of this pointwise product should be equal to the product of the image of each of the two functions f1 and f2. So this theorem tells us that all the pointwise products are strictly related with the functional maps. But let's see in the simple 1D domain what this pointwise product means. So if we consider the Fourier basis of this periodic interval 0 to pi, the first row are the first 5 Fourier basis functions, and on the second and third rows you can see the pointwise product of some of these functions. As you can appreciate, these product functions have high frequencies with respect to the first 5 Fourier basis functions that are considered. So the idea is, can we use this pointwise product of the Fourier basis function to better represent the high frequencies when we are trying to encode a point-to-point map in the functional map? The reason is that if we use together the Fourier basis and their pointwise products, we can better approximate a given signal on our domain. So in this case, the signal is the black curve on 0 to pi, and from left to the right you can see with a different number of Fourier bases the approximation of this signal depicted in blue. If we add to the Fourier basis also the pointwise product of them, we can obtain the approximation depicted in red, and as you can see, the pointwise product of Fourier basis provide better approximation of the signal on this simple domain. So what is the relation with the functional map and this pointwise product? So the pointwise product of Fourier basis cannot be represented as a linear combination of the Fourier basis due to the fact that the pointwise product is not a linear transformation. And so we can obtain an extension of the functional map to a new functional map C tilde that is able to transfer also the pointwise product of the Fourier basis. For more details, we refer to the original paper, Improved Functional Mapping via Product Preservation. But what I want to highlight here is that the matrix C tilde is composed by all value that only depend on the first eigenfunction phi1 and the value contained in C. So C tilde is a function of only C and phi1, so no further optimization are required to extend the functional map to a functional map that is able to transfer also the pointwise product of the Fourier basis function. So to visualize this idea, we can consider two shapes, M and N, and their Fourier basis. Then we can consider a functional map between these two shapes. And the new functional map C tilde is functional maps that is able also to transfer the product of the Fourier basis. Here we visualize a couple of product of the eigenfunction on the left, and you can see that the new functional map C tilde is a larger functional map that contains the original functional map C, but is extended to work also with the product of the original eigenfunctions. So, and thanks to this representation, we can encode the point-to-point map in a more accurate way, and we can recover a point-to-point map that has a lower error in the geodesic error evaluation. So to recap this algebra idea to recover high frequencies in the functional map, given on two shape M and N, we can compute and store their first k eigenfunctions, phi and psi. Then we can compute the pointwise product of all these eigenfunctions for the two shapes, and we can store them together with the original eigenfunction in a dictionary, phi tilde and psi tilde, and then we can try to represent the function defined on the two shapes through these two dictionaries. So the main problem is that the functions in this dictionary are not linear independent. So when we want to represent a function on a shape using both the Fourier basis and their pointwise product, so the dictionary phi tilde, we want to find a set of coefficients such that the function f can be approximated by the sum of as linear combination of the Fourier basis plus the pointwise product in this using this coefficient. But this representation is not unique due to the linear dependency of these functions, and so we need to add some regularization to estimate the coefficient. So we in the paper two main approaches have been proposed. The first one is to add p norm constraint to avoid that too many, so with p equal to 1 or p equal to 2, and with p equal to 1, we want to avoid that too many coefficients are different from 0, and with p equal to 2, we want to avoid that the absolute value of this coefficient is too big. The second approach is given by the singular value decomposition of the dictionary of a weighted version of the dictionary, and then we just use the larger singular value, and we recombine the composition of the matrix. And in this way, we are only giving a role to the larger singular value, avoiding the representation of noise. This is the main contributor of this approach. So as you can see, applying approach A, we can better approximate and transfer a signal defined on a shape using the same functional map. So we have the two shapes, their Fourier basis, and a functional map estimated for these two bases. The results are for the approximation and the transfer are the one depicted in the middle of the first row and on the left of the second row. If we add also the pointwise product of the Fourier basis and apply our approach A to regularize the estimation of coefficient in this new dictionary, we can better approximate the function and then better transfer it to the second shape without require any additional optimization. Here we have a video in which for an increasing number of Fourier bases, the signal on the left is transferred on the shape on the right. In the middle, we have the standard transfer obtained using the Fourier basis. On the right, we have the transfer that is obtained using, together with the Fourier basis, also the pointwise product of these functions. As you can see, from the beginning with few eigenfunctions, the transfer is more accurate with the product, and with dimension k equal to 65, we have a quite complete representation of the signal transferred on the second shape, while with this number of Fourier bases, a lot of information contained in the signal is not well transferred to the second shape. Here we have some quantitative comparison between the transfer with the Fourier basis and the transfer obtained with the product. And as you can see, the product representation outperforms the standard representation. The second solution to the high frequency representation problem that I want to present is based on the connection between the functional maps and the point-to-point map, and namely is the method, the zoom out method that was recently proposed. So starting with a point-wise map between two shapes pi, the idea is to refine pi in order to obtain a more accurate map. So this idea is referred as map refinement, and from the original paper of functional maps, several methods have been proposed to perform the map refinement. So the first method is based on the ICP in the spatial domain that was proposed in the paper, A Method for Registration of 3D Shapes, and it consists in the optimization for a 3D rotation that should, plus a translation that should align the 3D embedding of the two shapes. So we represent each of the shapes with its 3D embedding, and we look for a rotation that is able to align this representation to the same representation for the second shape with respect to the given correspondence pi. This idea has been extended in the original functional map paper to the spectral domain, where the two shapes are represented with the Laplace-Beltrami eigenfunction, so with their Fourier basis instead of using the coordinates. And again, the ICP in the spectral domain consists in the optimization for a rotation that is able to align the LBO eigenfunction of the first shape with the image through the point-to-point map pi of the LBO eigenfunction of the second shape. And the ICP method is an iterative method, and in the map refinement technique proposed in the original functional map paper, the ICP in the spectral domain is applied iteratively, solving for C and for pi. And this is done with a fixed size for the matrix C. So recently from ICP, new techniques have been proposed, and here we shortly derive one of the main map refinement techniques that has been proposed. So from the equation that is minimized in the ICP method, we multiply both the element with the pseudo-inverse of the matrix phi1, and then the product on the left is equal to the identity for by definition, so we can obtain this equation. And finally, if we represent the point-to-point map as a permutation matrix, we can write it as in this as in this equation. And this is actually what is used in the minimization proposed in 2017 by Daniel Jesus and Mira Ben-Hen. And the main aspect is that this is similar to ICP plus other regularization that we will see, but the main aspect is that they require to minimize this permutation matrix that should be a permutation that corresponds to a vertex-to-point map. A vertex-to-point map is a map between two meshes that map each vertex of the first shape to a point that could be a vertices of the second, or a vertex of the second, or a point inside the triangle of the triangles of the second shape. So this constraint to correspond for the function map to correspond to a point-to-point vertex-to-point map is an additional constraint that we want to exploit in this in our analysis. So in the blurring and the noising paper, they additionally propose to an additional regularization that is given by the constraint that the image through the permutation matrix of the eigenfunction of the second shape, phi2, should be spanned by the set of eigenfunction of the first shape. So this additional constraint is equivalent to ask that no spurious high frequencies are generated by the transfer, so that to remove the additional high frequencies that correspond to noise that can be added by the transfer from the set of function phi2. So inspired by this idea, we propose the zoom out method, and the zoom out idea is to obtain a registration of the two set of eigenfunction by progressively increase the size of the matrix C. And this, as proposed in the blurring and the noising paper, is done exploiting the connection between the functional map and the point-to-point map. So the main aspect of zoom out is that it is very simple to implement. It can be written in 5 lines of code, and the complexity of the zoom out method is similar to the one of ICP. So the zoom out algorithm is inspired by the ICP map refinement technique, and starting with an initial map pi between two shapes S1 and S2, and with an integer k, we can solve for the map CK as the minimization of the ICP equation, where we consider the set of truncated Fourier bases phi ik with I equal to 1 or 2, and this provide us a functional map with the same size k. So here at step 2, we are using only the first k eigenfunction of the two shapes, and we obtain a functional map of size k. Then we update the correspondence pi by taking the nearest neighbor in as we did for the standard functional map, but this time we use the functional map estimated at the step 2. Once we have to do that, then we update the value of k, and we increase this value by 1. With this new value of k, we can return to step 2 and iterate this process until a certain reaching some stop criteria. And the main difference with respect to ICP is that at each iteration, the functional map is converted in a point-to-point map, and then the point-to-point map is converted back in a functional map. This makes the functional map representation strongly related with the point-to-point map. Moreover, at each iteration, we increase the size of the map, adding new frequencies to the functional map representation. And this is exactly what we want to do, to add new frequencies to the functional map representation, trying to recover a more precise representation of the point-to-point map. So let me give you a visualization of the zoom out idea. So we can start with an initial map of size k that corresponds to a point-to-point map between two shapes. Then we can convert this point-to-point map in a functional map of size 5 and go and do that iteratively. We can convert back to a point-to-point map and then to a functional map, reaching higher and higher dimensionality of the functional map. And this will provide us a more precise point-to-point map. So as you can see, with size 50, we can obtain a more accurate point-to-point correspondence between the two shapes. Here we have a video in which the functional map of size 20 times 20 is visualized on the top left corner, and the transfer of the function from the shape 1 to shape 2 is visualized on the right. And you can see how adding new row and column to the functional map representation through the zoom out technique, we can recover additional detail in the transfer. I suggest to focus on the face of these two human bodies. So as you can see, after a few iterations, the signal on the face has been completely recovered, but also other high frequencies details have been recovered by the zoom out technique. So one important aspect of the zoom out technique is that its complexity is very small, and also for meshes with a huge number of vertices, the computational timing of the zoom out method is not large. So here I show you some qualitative results, and here the point-to-point map between the source shape on the top right corner is transferred to the target shape through different method. on the bottom row on the left, we have the initialization and then the refinement with different technique. And on the right of the second row, we have the zoom out result. As you can see, the texture is better transferred by the zoom out technique. Also, I would like to highlight the difference between the transfer of the initialization on the left of the second row and the transfer obtained with the zoom out technique on the right of the second row. Again, some quantitative results with respect to the other state-of-the-art refinement method for point-to-point map, and also the blurring and the noising method depicted in yellow. And as you can see, the zoom out method outperforms all the competitors. Finally, I would like to give you a visualization of the information transfer or functional transfer results obtained with different technique. So here we have on the left an original function f on the dog, and then we have the initialization using a small set of Fourier basis function on the cat shape. Then using ICP, we can better recover the signal, but a lot of high frequencies details are lost. And we can convert this functional map applying ICP to a point-to-point map, and you can see the not smooth transfer that is obtained by the conversion to a point-to-point map. Then we can compute ICP with a larger, starting from the same function, but using more eigenfunction. So instead of 30, I used a 300 eigenfunction, and you can see that some additional details are recovered but the function is not well transferred. Then we have the transfer obtained using the product, the method that we described in the previous method that we presented. And finally, the zoom out technique that is able to transfer in a meaningful way the signal from the dog to the cat, recovering a lot of high frequencies details that were lost by the other techniques. Finally, I would like to give a few words about a method that has been recently proposed. So the smooth shell method proposed at CVPR this year. And there are a lot of insight in the smooth shell method. So in this method, a fully automatic initialization is proposed, and also an extrinsic registration energy is involved in the optimization of a point-to-point map. And finally, extrinsic information are added to the representation of shapes with respect to the standard functional map representation that is completely intrinsic. But the reason for which I would like to talk about the smooth shell method is that it is based on an iterative scheme similar to the one proposed in zoom out. The main difference, as we said, is that in this case, the shapes are not represented only by the eigenfunction of the Laplace-Beltrami operator, but also the extrinsic coordinates of the smooth representation of the shapes are involved, and also the format version of the extrinsic embedding of the second shape. And finally, the normals as an additional extrinsic information are added to the representation. So what I want to say is that another way to consider the high frequencies is to involve the extrinsic information in the representation of shapes. So mainly this is due to the fact that the representation of shape given by the Fourier basis is the one that suffer more for the low pass representation, and so for the high frequency representation limitation. Okay, just to conclude my lecture, I would like to give a recap of what we saw during this lecture. So we described the functional spaces on 3D shapes and the Fourier representation of function on 3D shapes. And we saw that this Fourier representation is strongly related with the functional map framework that is a recent method to solve the shape correspondence problem. So the main one of the limitation of the functional map framework is that it is not able to well represent high frequencies. And I would like to give you a recap about why it is preferable to involve high frequencies in the functional map representation and why not. So it's preferable to avoid it because it makes the functional map estimation more difficult due to the fact that the size of the functional map is bigger if we would use also high frequencies. And the second reason is that the alignment of high frequencies is not easy. Also for near isometric shapes, the high frequencies Fourier basis function are quite different. Why we would involve high frequencies in the functional map representation of shape correspondence? The main reasons are two. So the first is that point-to-point map contain high frequencies. And the second one is that high frequencies are required for real application, like information transfer between two shapes. So in this lecture, we saw few different ways to recover high frequencies in the functional map representation. So the first one is given by the algebra structure of the functional space. And we saw that adding the pointwise product of the Fourier basis, we can obtain in a natural way an extension of the functional map, and high frequencies can be better represented using a dictionary composed by the Fourier basis and the pointwise product of these functions. The second way in which we saw that the high frequencies can be recovered is to exploit the connection between the functional map and the point-to-point map. This is done in the zoom out paper and also in the blurring and the noising technique. Finally, another way is to define new bases for the functional space that are not encoded by the eigenfunction of the Laplace-Beltrami operator. So there are several bases that have been proposed to do that, and each of them is mainly defined accordingly to the specific application that would be faced by these new bases. So this concludes my lecture. I would like to thank all my collaborators, and in particular Max Oksianikov, that inspired a lot of slides that I used in this presentation. I'm sorry if some part of this lecture is not clear. This was the first time for me to produce recorded version of a lecture, and I will be happy to clarify all your questions next Monday at 4 p.m. Thank you.